Should probably do a sound check. Can you log on to AoT BCS or take tx.ag/AoT live? And then
On here or on the phone?
on your phone. Because this is, oh.
So that they can find it.
Is it not?
Felix.
Felix! It says that we are.
Yeah, we are live.
Oh, okay, we are. Okay, well. Welcome, everybody. We have a great turnout tonight. We're going to start the show in about 5 to 10 minutes. So get a drink and talk to the astronomers.
Yeah, you're smart to come. I'm not like that either. I'm from New England.
Okay. All right. Yeah, I'm on scene.
Hello?
Is it working?
Yeah.
All right, hello everyone. We're gonna go ahead and get started. Welcome to Astronomy on Tap. Woo! This is our 50th time out here, so special event tonight. Today our trivia topic is going to be about our very special star, the sun. You have to click there now. Okay. If you'd like to follow us on social media, you can scan this QR code. You might have to zoom in a tiny little bit to get the QR code to actually work. And if you follow us, I will personally give you stickers. So incentive, I'm bribing you. I'll give you stickers.
We may or may not give you stickers anyway.
Yeah.
So as always, remember, help support the Grand Stafford, tip your bartenders, be nice, they're amazing to us. And you can, of course, always help donate directly to us. We have a cash donation box over there on the table, or you can Venmo at AoT BCS. A $15 t-shirt, $15 donation gets you a free t-shirt. A $10 donation gets you a free AoT mug. They're over there on the table if you want to check them out. I'm wearing the classic design. Justin's wearing our new AoT t-shirt. Yeah, they're nice. Those are double-sided, fancy.
Our next event is going to be September 28th. That's the fourth Wednesday, as always, in September. But today, in August, we're going to talk about the astronomy picture of the day, which is absolutely beautiful. This is the Cartwheel Galaxy as seen from James Webb. If you have ever seen the Cartwheel Galaxy as seen from Hubble, this is a significant improvement. Everything you are seeing here is basically just hot gas in this galaxy. Small pockets of stars. You're not seeing too many of the stars, you're just seeing the gas in this galaxy. So this is just unprecedented levels of resolution that we're getting from James Webb.
Yeah, JWC is incredible. You'll hear more about that later. As always, we have a number of astronomers in the audience. We have our new first years. Woo! Woo! So ask them all of your questions. Put them on the spot. And so with that, we are going to get to our very first talk of the night. We have, where is she?
She's down there.
Oh, there she is. We have Micalyn Rowe talking about archaeoastronomy. Fun fact about Micah, seeing as you know, this is the fun fact that we use every time. She has a dog. Her dog is royalty. She is, in fact, a princess. Her name is Beans.
Give it up for Beans.
Yeah, give it up for Beans. And give it up for Micah. Thank you very much.
This is all I needed.
Character water. You gotta take a sip. Okay. Make sure the lids are on yours. Okay, we're good. Okay. Good evening, everyone. My name is Micalyn Rowe. I am a fourth year astronomy graduate student here at AM. And tonight I will be talking to y'all about a really cool subject that I got to learn about in undergrad called Archaeoastronomy. Now, what is Archaeoastronomy? Basically, it's the investigation of the astronomical knowledge of prehistoric cultures. This is a really cool subject, and just a little bit of advertising. If you ever transfer to Texas A&M Commerce, they like these taxes on their undergrad. One of the professors has a super duper cool course that he teaches there about Archaeoastronomy, and instead of a final, you actually get to go on a trip to visit some of the like cool archaeological sites in New Mexico and Colorado. So I got to do that, and it was really cool. So based on that, today I'm going to be sharing a lot of pictures with y'all, and I'll be talking about the pictures and telling y'all information about basically the different historical sites around the globe and have some type of connection to astronomy. So to get us started, up on the screen, you can see that this is a picture of Paso Granada and Tahoe Canyon in the background, and that's New Mexico. And unfortunately, I did not bring my chocolates in honor of the talk today. I have my work on, but close enough. This is where one of the places I got to travel with my classic commerce, and I'll be talking more about this next week. Okay, so the first big site that I really want to talk about, we're going to start off in the UK. It's Stonehenge. It's pretty well known. This site was built around 3000 to 2400 BCE in the Bronze Age. And you can see that all these stones actually have a structure to them. And so this outer circle of stones right here, that's called the Sarsen circle. And then the inner stones, you can kind of see it makes like a little horseshoe shape. Those are called the trilithons. And then there's another type of stone within the circle called the altar stone. Right here. It's again where I pointed out on the inside of the horseshoe and all that. And so outside the radius of the circle, they're like way out here. There are these little bitty holes that are called auguries. They're really weird. They used to be filled with cremated remains. But now they're silver chalk, so they're just like these teeny tiny little white holes that surround the Stonehenge. And then the last important structure that I want to mention here is something called the heel stone. It's actually not pictured out here because it's a little bit farther up. If you look to the top right, that's about where it would be. Yeah, we'll see. It has a special alignment that is connected to astronomy. And so here you can see the Joseon is the little rock right there in the middle. Our point of view is from the altar stone. And so on the summer solstice sunrise, the summer solstice, just for some background information, is like the longest day of the year. That's when we get the most daylight. If you could stand at the altar stone and look toward the heel stone at sunrise, you would see the sun rising directly over the heel stone. And then vice versa, on the winter solstice, the shortest day of the year, the sunset would align if you started to build something and look for the altar stone. Solstice alignments are actually pretty common in ancient cultures, so it's very easy, it's something that they all experience. And so another cool thing about Stonehenge is that the structure wasn't actually alone. There's another structure in the UK that they kind of like to term as Woodhenge. It's located in the United Kingdom around German walls. I'm showing off in a second. You can kind of have an idea of where it is. Unfortunately, because it's made out of wood, it didn't preserve as well as the stones, and we only know about it because of excavated remains. And so here's a map of the area for reference. Stonehenge is like right here at the bottom of the center. And then to get to Woodhenge from Stonehenge, they would have like made a little track from each side. They would go here along Stonehenge and So there's the river, the travel water, we want river here, other those during avenue, and so there's the during wall here. So the Jersey wall was actually just like a huge circular trench, and this is where Woodhead would have been located. And there's also this weird feature that no one knows why it exists. They don't know how it was made. They just don't know anything about it. It's full of prisons, and it's a big, weird, rectangular plot of land here. And yeah, no one knows what it's for. And then we're going to move a little bit up to Ireland to a site called Newgrange. This is actually a burial mound that was built around 3100 BC. Lined up in the front, right here, these are called curved stones, and they are elaborately curved stones with spires. And you can see an example of these real big curved stones here on the left, and special like part of structure on them. And then here on the right, we have two different viewpoints of the burial. And so the top is like a top view. You can see it's tunnel and it's shaped like a cross. The cross actually points southeast to line up with the winter solstice. Like I said, they like to line stuff up with the solstice. And so this is a burial mound, and so the bodies were kept in the leaves of the cross. And then on the bottom side of the picture is a side view mound. This little structure right here, that is called the roof box. And what this little roof box does is it lets light from the winter sunrise into the tunnel. And what happens is the tunnel is actually built on a slope, so that when the sunlight shines through the roof box, it actually hits directly the bottom of the cave. So yeah, next we're going to travel more southeast to the Egyptian pyramids. And fun fact, all the pyramids are on the west side of the island. And this is because the west side represents death, because of some steps in the west. And so first, ancient Egyptians used mastabas, which is an underground burial chamber to bury their dead. And then they started to move to the above ground burial chambers here. And so here's the picture. These are actually the Great Pyramids of Giza. The entire reason that the pyramids were built was to get the pharaohs to the afterlife. Their attention to detail in building these pyramids was insanely precise. For example, when they were building and constructing the pyramids, they actually used a cornerstone on the southeast corner to line up the entire pyramid with the cardinal directions. And they were actually pretty dang accurate. Again, they only used one stone out of these ginormous pyramids to line up the entire pyramid. How they did it, we don't know. How they even built the pyramids, yeah, we don't know. But it's pretty dang cool. Yeah. Go talk to Justin if you want to learn more. So the Egyptians had some pretty cool astronomical alignments built into the structure of their pyramids. This is the interior shown here of the Great Pyramid of Khufu. It was built in 2554 BCE. The entrance is on the north side, but the most interesting thing about this is basically the different stars that the air shafts, like the volcanoes that have pointing to something, the air shafts. So the bottom left air shaft right here points to Sirius, which we know as the brightest star in the sky, but it's also known as the eye of the dog, aka the eye of Phoenix nature. The top left air shaft points to Orion's belt. And if you don't remember, Orion's belt is a series of 3 stars within the constellation of Orion. And so this is, pretty well known constellation. The top right air shaft actually points to a star called Thupin, which at that time was their North Star. And so the star is also known as Alpha Draconis, which I just thought was super cool. And then last but not least, the bottom right air shaft actually points to Kochab, which is the brightest star in the bowl of a Little Dipper. Moving farther east, we can also find astronomical history with Polynesian wayfinders. And so yes, this is like the people from the movie Moana. The Polynesians would actually sail super big distances and would navigate the Pacific Ocean from Hawaii all the way to Fiji. Their navigation techniques have been used with the stars, they use the currents, waves, and also actually birds. The specific technique that they used was to deliberately sail east from the east of an island, and then once they reached the correct latitude, remember latitude is basically the lines that are parallel with the equator. So once they reached that correct, I'll use it sometimes, really the correct latitude, they would then travel straight west until they hit the island. And how they measure their latitude, they actually, like in Moana, they use their hands to help measure their position. And they would measure it against constellations or stars in the sky. And then finally, we're going to hit some of the Americas. This is Choco Canyon in Mexico. This is one of the sites that I got to travel to. This area was inhabited by the Amazon people. And this main Amazon was actually given to them by a Native American and the ancient ones. Their structures were built around 950 to 1150 AD. And then this picture specifically is Bahana Butte. Remember the structure earlier. This structure right here in Puerto Bonito, we actually got to go inside the structure, and so that was pretty cool. There's a meridian wall, and a meridian wall is basically something that points north-south, and that splits the semicircle in half. These big round rooms called cuboids were big circular rooms that were underground. They were covered with wood, and they were actually used as a gathering place for the 100 people. The wood that they actually used to build the different levels is how people were able to date these structures that they built. And they actually made like really short doors. I'm a pretty short person myself. I'm like 5'1", but the doors came up like right here on me. So like they were pretty short. And then weirdly enough, when the Amazon people left these structures and migrated somewhere else, they break in the doorways, and again, we don't know why. People do weird stuff. This structure was also in Choco Canyon. This is the picture that I had up on the very first slide. This is Choco Canyon. This is otherwise known as a house with no corner. This is one of the what they call great kivas. This is actually a pretty decent walk away from Puerto Rico. Maybe like 7 miles, don't quote me on that, but about astronomers' approximation. You can see here they have 4 big poles that will hold, that will be big wooden posts to help hold the roof. Then they also have each in the walls, where you can kind of see the small little holes. These are poles, and then again, really big solstice lineups they like to use. So on the summer solstice sunrise, there's a little bit of window that the sunlight will shine through just right enough that it can shine right into the Great Kiva. Remember that structure that I told you all to remember how to use? This is on the inside of the body. We don't have to head to the top of it. There's these spirals carved into yellow rock. And different the ways that the sun lines up, you know, like the equinoxes or the solstices, cause light to shine on these spirals in different ways. And how they actually made this happen is, again, I don't know how they did this, but there's these huge vertical, really skinny rocks that are leaning up against the side of the hundreds. And they're really big. I don't know how to use them or how they move them, but they help create these sort of light. So on the summer solstice, this little light dagger entered in the center of the spiral. On either of the equinoxes, the light dagger entered in the center of a small spiral, and it's so tired of hard to see, it's right here. You can see it better here, obviously. You can see the color right there. That's where the light dagger ends up on the equinoxes, and then on the winter solstice, the light dagger ends up on both outside of the spiral. Here in the bottom. Another thing that we actually got to to in Choco Canyon was the supernova technical. If y'all don't know, the supernova is what happens to a star at the end of its life. It explodes huge, massive explosion. And so the reason that this petroglyph was preserved so beautifully and why you can actually still see it today is because it's actually painted on the other side, ceiling that's sticking out of the cliff face. And so, erosion or wind or dust or water, none of those things are actually wash the petroglyph off. We think that it's depicting the July of 1054 AD supernova that Chinese astronomers actually saw and were able to record and write down. And so that is why we have such a specific date for when the supernova happened. And we also know today that that's what that was the crowd nebula, that's when the crowd nebula blew up. Moving down on to Mexico, this is built around 100 BC, which means City of the Gods. This actually predates the Aztecs. This road we can see right here, it's not straight north and south, it's actually 15.5 degrees east and north. This road is called Avenue of the Dead, and the orientation of the pyramids to me is kind of wonky. A lot of their civilization kind of worship the sun because it's a source, it's a power source to their crops, kind of a life giver. But actually the pyramid of the sun is to the side of the road, and then the pyramid having the moon, you have to the big one. The north side of the sun ends with sunrise on February 9th, and it also lines up with the sunset on April 30th, August 13th. And we don't know why these specific dates. Usually people like to line stuff up with something, as you've seen, but we don't know why these specific dates. There's another site in Mexico called the Yaswant. It was theorized to have been built around 1325 AD. It is supposed to have been built on Lake Texaco, the Aztecs actually built this structure. Their beliefs said that they should build a city where they saw an eagle eating a snake on a cactus, which is super specific if you ask me. And they said if you did this, if they built a city where they saw this happening, then they would grow and be a great empire. The company one was very organized, and all of the roads are lined up north, south, east, west with apartment directions. This is a mock-up of what their central plaza area would have looked like. And if I butcher these names, I'm sorry, please forgive me. The blue temple here, right here on the left, is the temple of Lambo, which was the god of rain and fertility, and the red temple on the right, which is the temple of which is their god of sun and warmth. The whole thing, the whole structure is actually called the Temple Mayor, and then from the new platform, which is a kind of circular area right here, if you stood on that, on each equinoxes, the sun would rise directly between the blue and the red temples. I'm going to enter, we move for the south and through to the side of Machu Picchu. Machu Picchu was created by Inca. It was actually found by Kieran being the third, who was expeditioning to specifically find gold in cities. This site wasn't actually used for very long at all. It was used for about 20 years, from 1438 to 1472. 30 years. This is actually used as a summer palace, so it worked beauty. And then one building in particular is interesting to us from the astronomical point of view. This is the Florian, and there is a window that casts this kind of what I call a light shadow. I don't know how better to say it. That points towards the rising of the deities. And then this window on the right here, it's not, sun's not shining through right now. But the window here points to the rising of Polka, which is the last two stars from the tail of the concept of Florida. And lastly, I actually got to this site as well. This is Mesa Verde in Colorado. If you have a chance to go check it out, I very, very highly recommend it. They have really good ones that will be next to underneath the cliffs to protect them from weather. And yeah, they're really cool to look at. And there's nothing more information on them. But if you have any questions,
Thank you so much for listening. Does anyone have any questions? Yes, ma'am. These pictures were found on a lovely Google. I actually have a reference slide to all of them. I was, too busy experiencing and I didn't spend enough time, taking pictures, unfortunately. And also it was really hard to get some really good, like, top-down viewpoints. So yeah, unfortunately, these are not my pictures, but they are printed here on the slide if you would like to learn about it. Pueblo Bonito, the semicircle one, actually, you can actually do a hike up this cliff, and it's supposed to actually overlook some Pueblo Bonito, and so we actually did get to do that one and kind of do a top-down look at that one. But for others, like, you're not allowed to go on the Baja View. You're not actually allowed to hike up it anymore because they're trying to preserve, the rocks and making sure that the giant rocks that I talked about don't like stand down on anyone. So some of them you can hike to, but some unfortunately not. Sorry, Thomas. So the question, I'm sorry, I forgot to repeat, for you. The question is, why do all these different cultures, basically, why are the solstices significant to them? The easy answer, the true answer is that really it was just like one of the easiest things to tell out of their experience. Since ancient cultures, they actually did a very good job of basically tracking the seasons and everything, for their crop cycles and everything. And basically the solstices were like one very easy pattern for them to pick out and like, worship or celebrate. So that's the reason. Thomas, what's up?
You said like during the slide and then remain.
Yes, yes.
And you said it wasn't.
So, okay, yes. So Thomas asked me about the Audrey poles that I said were filled with remains, but then now they're filled with chalk. Stonehenge is a very popular tourist site, and so they do want little kids sticking their hands and getting cremated remains all over themselves and stuff. And so they decided probably to take some of it away and like study it as archaeologists do, but mostly just to keep in, for the bones safe. They replaced the remains with chalk, just keep it safe and yeah. Any more questions? It's hard for me to see in the very back, so. Oh, yes. The question is, we're on the structure at Machu Picchu that I showed. There are two main windows that I talked about. Is there any significance to the other windows? As far as I know, I don't think there were. Yeah, but I don't have a direct on this video for many years since I've studied it. But if I can remember correctly, no. Great question, great question. So he said that I mentioned that, certain, windows or air shafts or something, they would point at, specific stars or, things in constellations. And because of the movement of the Earth, they would point to these things at different times of the year. Which is very true. I forget exactly what time of year that, like, for example, the pyramids of Egypt line up with these specific stars. Yeah, I forget. But I will say, for example, Thuban, the North Star, way back then. Of course, it would point to that star all year round because it's our North Star, it's always in view. Of the Earth. Yes. I think we're good. Thank you all.
Oh, yeah, let's thank Michael one more time. So next up, we have trivia. We have a couple of people walking around. If you would like trivia, can you please just raise your hand? We will have some people drop off trivia sheets and pencils for you. If you are an astronomer, you may not do trivia. First year in the time sheet. Freshman. Did you meet Felix? That's what she wants, right?
Yeah.
I met her.
I met her.
What is her name? Did I even introduce that? I can't.
I met her at the graduation reception for the family. Yeah. And he was like,
For a second, when I first saw her, I was like, oh my God, it's married to Rosalita.
something in my head says Amy.
No, I don't think that's right. I'm gonna ask her.
She's gonna be something like that. Some assumption.
Because. Is that Linda?
Yeah, I think it's.
All right, does anyone not have trivia and would like a trivia sheet? Kayla, no cheating. I can see. Does everyone have a pencil? Does anyone need a pencil? Okay, all right, we're gonna go ahead and get started then. Our first question, what percentage of the mass of the solar system lies in our sun? A, 99.86%, B, 82.45%, C, 68.86%, or D, 54.97%. As an astronomer, this hurts me because these are all the same percentages. We'll go back. Of course, it's my friends anymore. Ashley, no comments. All right, next question. What is the most abundant element in the sun? A, helium, B, carbon, C, hydrogen, or D, iron? What's that?
Reversers are actually.
I don't, I think they're at the bottom. All right, what causes the aurora borealis and aurora australis? A, the earth spinning slightly faster as it gets closer to the sun. B, solar winds interacting with Earth's magnetic field. Or C, aliens using Earth as a screen for movies. And if you were at my coffee,
It's always aliens.
it's always aliens. Question 4, how hot is the core or center of the sun? 25 million degrees Fahrenheit, 3.5 million degrees Fahrenheit, 10,000 degrees Fahrenheit, or D, not sure, but definitely not as hot as a Texas summer. I don't know. I know it's long. Okay, I thought so. All right, question 5. What is the name of the spacecraft sent to study the outer corona of the sun? A, the Solar Corona Investigative Mission, or SCIM. B, the Parker Solar Probe, or PSP. C, the High Energy Landing Probe, or HELP. Or D, the Galileo Solar Spacecraft, or GSS.
For the regulars in the audience.
The regulars.
Remember my news saw from a month ago, you know the answer to the question.
I was here. I don't know the answer to the question.
Question number 6. How old is the sun? A, 10.5 billion years old. B, 4.5 billion years old. C, 1.5 billion years old, or D, 6,000 years old. Question number 7. Please don't get this wrong. The sun has a magnetic field, true or false?
Options. Trick question.
Question number 8. When does the solar eclipse occur? A, when the Earth casts a shadow on the moon. B, when the Earth is in its closest point of orbit around the sun. C, when a solar storm clouds the sun's surface, making it appear darker than normal. Or D, when the moon obscures the sun. Question number 9. Where does the sun lie in the Milky Way galaxy? Is it A, in the central bar? B, in the very outskirts? Whatever that means. C, in the helio arm, or D, in the Orion spur? And our final question for question number 10. When will the next total solar eclipse occur in North America? A, June of 2022. B, February of 2023. C, April of 2024. Or D, November of 2024. For those interested, it will be going in totality over Dallas. So you don't have to go that far. It's also going by Dallas. Yeah. Does anyone need any of the 10 questions review?
Which ones?
Anybody? Yeah, please. 5, 9. Back to question number 9. Where does the sun lie in the Milky Way? The central bar, the very outskirts, the helio arm, or the Orion spur? Anybody else? Any other questions being repeated? Everybody is highly confident in their answers. And everyone is on 10 out of 10.
If you do, it's gonna be an awesome rock, paper, scissors.
We will have a 50-way rock, paper, scissors society. Wonderful.
All right, so now we are going to take a 15 to 20-minute break. So you can fill out the backs of your trade sheets and hang out, talk to the astronomers, refill your drink, do what you gotta do. Please talk to the astronomers. We'd love to answer your questions. We're lonely. We are lonely astronomers. So yeah, so we're gonna start now in like 15, 20 minutes. We'll get back to it.
When you are done with your trivia, raise your hand, yell at an astronomer, they'll come pick it up. You can hand them to them at the table.
Plug that for a second and take me to the answers.
No, I think I got it.
You got it. So you're gonna grade.
No, we should
I'm
give that to
talking
Caitlin.
next.
Okay, give them to Caitlin. You tell her your
I,
boss.
here,
Just for the answers, so she can write all the
okay,
answers.
can you tell me the answers? Nicole?
Okay, ready? A, C. A. Yeah, you have them right here. A, C.
A, C,
B, B.
B, B,
Yeah, B.
3B.
Four B's, actually. Yes. Four B's. Next one's a B. D. Or no, sorry, A. D. D. C. And then just
This one I
write
think
answer
it's
key and give it to Caitlin,
Hold on.
because you're the boss lady.
Yeah, I am.
Oh, no, sorry. This is A. Question 4 is A. My bad. That was the only one I didn't know.
You're doing that on.
A, C, B, A.
You're just like. Flip through. All right, everyone, we're gonna go ahead and get started again. Up next, we have In the News with Nikko. Fun fact about Nikko is that he is from Connecticut. That's it. That's the fun fact.
Thank you. How's everybody doing? Yeah, it's not really exploited. So today, we're going to talk about some really interesting news. We're going to talk about some drama. Just wait till the end. But first, we're going to talk about sending some fake people to the moon. So, days, August 29th, hopefully with some backup dates, September 2nd or September 5th. The Artemis 1 rocket will be carrying the Orion spacecraft, which will go up to the moon, orbit around the moon, do a bunch of science, take a bunch of data, and then come back. This is an uncrewed mission, so there will be no humans. What will there be? So I said in the title of the previous slide that they will be some crazy humans. So what do I mean by that? So this is an artist's depiction of the Orion spacecraft. And it has a pretty interesting payload going along with several other science instruments. There will be 2 mannequins. I'm not making this up. There will be 2 mannequins whose sole job will be to exist, to get pounded by radiation from the sun, to see what happens if you're left out in space for a month, which I thought was pretty awesome. So be on the lookout for this in the next, what is it, August 24th? In the next 5 days, it'll be confirmed or denied for August 29th. You can watch it on, whatever your favorite streaming platform is, nasa.gov. I'll go over, a couple of smaller stories from this week, as I like to do. We have first the chunkiest star known to many was not as chunky as we thought it was. In fact, this star, which I will read its horrible number name, R13681, was originally thought to be about 300 times the mass of our sun. But it has now been confirmed to be in the range of 170 to a measly 230 times the mass of our sun. So that's tiny in comparison. It's actually still the largest star, most massive star that we've ever measured. And this, flying spaghetti monster thing on the right is actually, anybody recognize this from high school chemistry, biology? Aliens. Yes, aliens. So this is this is an RNA molecule. And so aliens were found in the galactic center. What I actually mean by this is there were complex organic molecules, which are basically the building blocks of RNA that were found in the central molecular zone, basically a fancy way of saying a cloud of stuff of molecules that is in the center of the Milky Way. So life, aliens, I think so. The moment you've all been waiting for, you really didn't think that you were going to get out of in the news with Nikko Cleri without hearing about JWST. So this is this lovely 6-meter telescope that is, flying out in space, way out there at altitude. And there's been some drama. I talked about a little bit of drama last month, talking about the highest redshift or furthest away galaxies that have ever been measured. So as a refresher, the term redshift, also denoted by Z here, is essentially if you have things that are further away from you, because the universe is expanding, things that are further away from you are expanding more, so they appear red. That's what you see in this sort of Doppler shift as this galaxy, the ball of light there, moves further away from our Earth. So the drama comes in when a bunch of people started publishing a bunch of papers that said that we had discovered the new most distant galaxy. And these came out, day after day for a period of about a week or two. Basically, everybody was like, no, you're wrong. Mine's farthest away. No, you're wrong. Mine's farthest away. So in terms of, if you look at the top axis here, this is, unit that look back time. So if the universe is 13 point something billion years old, we're looking at light that is also 13 point something billion years old. So we're looking at galaxies denoted by these, I don't know, whatever color that is. Stars. What was that? Magenta? That's a good color. So these nice magenta stars denote each of the new detections, supposed detections of each of these new contentious galaxies. And I've labeled this one right here, which is my favorite of these, which is that red 14, which is drop that up there, 13.4 billion years look back on. Ridiculous numbers. This galaxy is affectionately referred to as the Navy galaxy. It is named after the daughter of Stephen Finkelstein, who's a professor at the University of Texas, because it was discovered on his daughter's birthday. So he named it after. So we like that one. We don't really like that one. Nobody likes that one. Some people came out with a paper that said, hey, we have these things which are way past everything else that anybody else has ever seen. And the rest of the community was basically just like, no, you wouldn't. So we're going to ignore that one a little bit. We're going to talk about a little bit more about the drama behind this. So thank you, Jordan. So what is this interesting? So this was originally published to be at, redshift a lot, redshift 72 or so. So less than a couple 100 million years after the Big Bang in terms of look back. And so my collaboration, this year's collaboration, thank you so much, put out a paper basically saying, no, actually, calm down, you were wrong. So this was led by Professor Silvana. The title of this, it's a very poetic title. A dusty starboard masquerading in ultra high galaxy in JWST Sears observation. So led by Jorge and the rest of the Sears team, just a casual 120 authors. In case you're curious, that's me. And there's also a couple other people in the crowd. Yeah, really making names for ourselves as 50-second author. So this paper basically came out. It said, if you look at pictures of this galaxy in order of increasing wavelength of these filters. So I talked before about redshift. Think of left here as blue, right here as red. So these things, as you can see in the first two panels here, you don't have this blob until you get to this panel. And so we're getting no light coming from the blue side and some light, actually increasing amounts of light as you go further to the red side. So this is one way of determining how far things are when they start to show up in space. And so this, I'm not going to get into too much. The bottom plot is what's called an SED, spectral energy distribution. And sort of the contentious point here is, I don't know if you can read this too well, but if you fit this line or 50 data points, you can get an estimate for what the distance to the galaxy is, what the redshift of the galaxy is. And you can see these numbers are wildly different. The important points, so 5, 5, 5, 18, 17. The numbers, the bits that come up with 18 and 17 are only using these points. Which, if you zoom in on this inset window, it's such a small region. But if you fit it with 4 points in a really small range, you do get something that matches to a redshift of 18. It's ridiculously close to the big ends of the galaxy. But what this paper is arguing is, if you actually include all of the data that we have, you get something that's much more reasonable, like 5. So I think this plot is hilarious. What you're seeing here is the probability distribution function. Essentially, bigger peaks means more likely. So we see a peak here at redshift 5, or peak here at redshift 17 or so. This is, if you take into account all of the data, which is what this paper is doing, this is what happens when you only look at that one small little sliver. And so everybody was, up in arms about a lot of these papers that were basically saying, we're discovering all of these incredibly ridiculous things, which essentially mean all of our understanding of the early universe is wrong, which it is, but not for these reasons. So I like to end this TED talk by saying, science is going to remember what was right, not what was first. So in many years from now, all of these papers are going to say 2022. Nobody's going to remember that it was, July 17th versus July 19th. So I'll end my sermon by saying, take your time, do things right, be remembered for doing things well, not doing things quickly. Thank you. And that is what's in the news. Does anyone have any questions? Sure. Aliens. Yeah, so basically, I don't have a picture of it, but if you imagine our galaxy, which, in simplistic terms, is, maybe something like this, right? You have a central dome, you have spiral arms and stuff around it. Right in the middle, there's something that we call the central molecular zone. So when you're in the middle, you have a lot more stuff, concentrated, and it's actually there are certain pockets that have extremely high densities of, molecules. And so, if we look at those specific slices of the sky, we can actually see the things I guess in this picture, it would be, kind of these little red guys, or the individual little green guys, basically the things that build up this much larger and much more complex molecule. And so essentially what that's saying is there is stuff out there in space that is ready to create life as we know it, but we haven't seen it there. But it can be there. We know the building blocks are there. So yeah, that's a good point. What you're seeing, actually, if I go all the way over here, so what you're seeing on this plot is, time on the top axis. So the Big Bang would be, all the way over there. Present day would be infinitely over there. Well, depends on how you plot it, whatever. So the present time is what's called vertical zero. So that's right here in space. We really don't have that big of a difference between here and the center of the Milky Way, as opposed to here and these galaxies that are the entire universe away. So the center of the Milky Way is 8 kiloparsecs, so 20 something light years, 20,000 light years away. These things that we're talking about are, well, tens of billions of light years away. So yes, you are correct that they're reaching us. The light that was emitted from them several thousand years ago is reaching us now. But several thousand years in terms of astronomy is instantaneous. That's a great question. Anybody else? Yes. That's fine. I don't know anything either. I'm just up here with the microphone. Yes. That is a wonderful question. The light quote unquote ends when it hits. Otherwise, it would go forever. If forever makes sense. But yeah, that's a wonderful question. Light will go until it interacts with something, and then impart its energy onto that thing, and then that light is quote unquote. Wonderful question. Yeah. Yes. Yes. That is an effect called attenuation. So imagine like if anybody's seen like spy movies where they have like the lasers going through the room and they take the thing of baby powder and they throw it and all the lasers go up. What's happening there is the light. I'm getting my Oscar accepted to get off the stage. So what happens there is the light hits the baby powder or whatever. In space, it would be things like dust in the galaxy. And so that light then gets scattered off, and that's why you can see the beam of light, is because it's not just going straight through where it is. So yes, if you're looking at something that is way far away, there is an almost 100% chance that a good amount of that light is not actually reaching you because it's getting stuck in between you and that. Justin had to take a call. It's more important. Okay. So we're having fun. We're learning things. Go ahead. Yeah. What is the alien thing called? That thing? Oh no, it's like a new one. That thing is called ribonucleic acid. So that's RNA. You might also be familiar with DNA, which stands for deoxyribonucleic ribonucleic. Fancy science, fancy chemistry. Yes, they're not actually that big, they're not like size. All right, thank you, everyone. Oh, I guess I have to stay up here, sorry. Coming up next is our final speaker of the night, talking about gravity. Yeah. It is our whatever official title, President Supreme Leader Silvana. And a fun fact about Silvana is finding change her life. And I'm sure she can tell you more about that. Give it up for Silvana.
Yeah, let's start with small right now. How many times? Yeah, I was reading nervous about this because I'm talking about gravity. There are physicists in the room who know a lot about this. but I wanted to explain it in layman's terms for the people that are not physicists. And also to give a perspective on how I view gravity, because I think it's really cool and it's fundamental. It's very fundamental to how we view things in the universe. So that is why I'm going to talk about the gravity of our universe. And that also came from like this gravity situation. Like it's kind of like a lot, right? But now I'm going to talk about gravity of our universe. So don't follow me on my Instagram. It's kind of embarrassing. I post a lot of pictures and sometimes follow Nikko on Twitter, don't follow me on Instagram. But I do have a really cute dog. And I post pictures of her, so if you're interested in the dog content. All right, so there's a drinking game. So like, if you don't have a drink right now, feel free to get up, go to the back and order a little drink. So you can drink every time you hear the word gravity if you want a challenge. Or you can drink every time Albert Einstein is mentioned or Sir Isaac Newton. So you choose which one of these you want to play. So yeah, so you might have heard of gravity before. You might have seen pictures like this, where objects are in space-time continuums, and I'll talk about that in a bit. You might have heard of Einstein. You might have seen pictures like this, where you have stars and galaxies or whatnot. You might have heard of the movie Gravity with Sandra Bullock. Interstellar. That was a big one where they actually showed a supermassive black hole. A theoretical one, of course. But what is gravity? And I'm going to try to explain that to you today in layman's terms, of course. So gravity is force. What exactly is a force? So a force is kind of just like a push or a pull on an object. And it's given by this equation, M equals ma. It has a magnitude and direction, and I'm not going to get into that. But essentially, if I'm an object and I accelerate, change velocity over time. But if I accelerate and I try to like push on something, like Justin, then Justin with the tattoo, so asking about it, Justin with the tattoo is going to feel a force, which is essentially a push or a pull on it. If I accelerate fast enough, I can push him over, right? So what that means is that with a bigger mass or a bigger acceleration, I'm going to have a bigger force. So that's just like the definition of a force. So there's 4 fundamental forces in nature. And I really don't want to get into these because the physicists know much more about this, but we have the strong force, and that kind of binds matter together. Just gonna leave it at that. We have the electromagnetic force. That's when you have like a positive magnet and negative magnet and positive and positive pushing against each other. Field force against them. The electromagnetic force acting. We have the weak force, which is responsible for how subatomic particles behave. So particles just like, I don't know where it's like decay into more particles. That's the weak force, it's weak. And then we have the gravitational force, the weakest force. Did you know that? Yeah, now you do. Okay. So gravitational force, force of gravity, what we're talking about, it's the weakest force. So why is it so important? I don't think you understand the gravity of this situation. Why is it so important? There's a lot about gravity. Like if there wasn't gravity, we would run in space. But that's not actually how gravity works. It's not like because of gravity we would float. Like we wouldn't go. Just a meme. Okay, let's see about the thought experiment, because before cell phones and technology and things like that, people would think. In their free time, people would just think. And we have like a classic Newton owl falling. And oh my God, there's owls falling in my head. Flying away. No, it's not flying away. It's not flying away, it's gravity. So briefly, very briefly, how people started to think about gravity. Early 1500s, Galileo started to test the effects of gravity, and he threw things from the Leaning Tower of Pisa. So he would throw two different mass objects, so objects of different masses, and then he found that these objects, although being two different masses, one heavier and one lighter, got the same acceleration. So they accelerated at the same rate. Which you would expect the one with the more mass to accelerate faster. So that's kind of where it started. But then Sir Isaac Newton, did anyone get Derby's? Oh, cheers. Yeah. All right, yeah. Okay. Sir Isaac Newton and Einstein. Remember that. Okay. So he established the law of universal gravitation and like in the late 600s. And that's when like the falling apple idea started to come out. So he was like thinking about like things like fall. It's kind of really crazy to think about it. Like you don't float, you just fall. And so it's like, what if the moon is falling around the earth? So that's what we need to think about without his cell phone and his Wikipedia. And that's it. The Newton's law of universal gravitation, which I'll explain in a little bit. And then Einstein came about a few hundred years later. The time scales are really short, even just like 100 years later. And he established the general theory of general relativity in the 1900s, which was like a huge thing that he had to prove, and he tried to do it based on the solar eclipse of the moon, but it didn't really work. So there's a whole documentary about that in like National Geographic. You can look it up. But that was Einstein's theory. And that's what the modern physicists kind of like take into account today in terms of gravity. Okay, history. People move. We can't like jump up. I like jumping. It's like we can't jump up, we fall. Well, what is it? What is gravity? We don't really know, but we know how it interacts. Okay, we know that it interacts with things. So I'm going to explain what gravity is by NLAW, which is Newton's law of gravitational. Newton's law of universal gravitation. Okay, we can say that to your friends, sound smart, and if you mention this equation, and if you don't understand this equation, if you've never seen this equation before, or if you've never seen the physics class, this is your moment. Okay, you have the force of gravity is equal to m times m1 and m2 over v squared times v. So let's do an experiment. We have the mass of the sun and the mass of the earth. So those are two different masses. Okay. Ooh. Spoilers. Okay. So the mass of the earth, mass of the sun, and then it's inversely proportional to the distance between them squared. So the more massive an object is, the larger the force of gravitation. Okay, so there's two masses, there's like more gravitationally attractive. And then if you separate those masses, those weaker the force is going to be, but that's squared. So that's like times the distance of itself. speed times speed. That's what these squares mean. So the further away objects are, the less the gravitational force between them is going to be. And I have the number 1, and who wants to answer why the number 1 here is? What is 1 between the Earth and the Sun? And actually, astronomers like to measure things in astronomical units, which is just the distance between the Earth and the Sun. So if you want to sound smart to your friends, you know, yeah, the Earth and the Sun are one astronomical unit. But anyway, that's their distance. And then we have the gravitational constant G, which is very small, times 10 to the negative 11. So this is a very small number, but it's necessary in order to measure this gravitational force. It's just a constant, as we call it in astronomy and physics. So yeah, and look is romantic. Okay, 2 masses, you can measure the gravitational attraction between any 2 masses. And okay, maybe you solve 2 variable particles. Fine. But it exists, you can measure it. So yeah, the Earth and the Sun fall up. They're gravitationally attracted to each other. So you can say something like, oh, I'm so gravitationally attracted to you. Yeah, that's exactly what the Sun does to the Earth. Yeah. Okay, but there's a problem. N1 does not explain why gravity exists. It's just kind of an equation. You have 2 masses, you have a distance between the 2 masses. Okay. So our Einstein, very important human being that everybody in the room knows, and everyone should be drinking. Yes, yes, you do. He came up with Einstein's theory of general relativity. And so what this is saying, if you've never heard of this before, if you've never like thought about this before, is you can think of this like geometric configuration or a sheet. It's like a small sheet. And when you place something on that sheet, it's going to cause events in the sheet, right? Like you think of like a feather sheet. If you place a more massive, more dense object on that sheet, it's going to cause a large event, right? So that's what you can see in this figure here. More massive, more dense, going to cause a bigger curvature. And what astronomers like to say in astronomy terms, I don't say this in scale, is this is causing a curvature in space-time. So the more massive an object is, the bigger the curvature in space-time is, and the larger the acceleration. So that's why we're all falling, right? And that's when we have an acceleration of gravity on Earth and on different planets or the moon. But I really like this quote by John Wheeler, which says, mass tells space-time how to curve, and space-time tells mass how to move. So if you have a big mass, or dense mass, causes a curvature in space-time, like that. So more mass object would be like that, a visual learner, you can tell. And so this big mass will help space-time how to curve, but then space-time will tell other masses how to move. So if you're a smaller mass, then you will move at a different acceleration due to the bigger mass. Which is happening when we're here on Earth. You can test this out in your bed with your dog. So if you're in a bed or in a couch with a different being, a different object, I just can't stop laughing. Okay. Okay. So if you're in a bed and there's a smaller object next to you, or vice versa, if you're like a smaller object, then the smaller objects will like gravitate towards you. Have you felt that? You've experienced that. I'm the smaller object in this scenario. I've definitely like fallen into the big one. Sometimes I've fallen into the big dog. It's just like an interesting thing because then you can see like how these like physical phenomena like are applicable to your day-to-day life. Like that's essentially what's happening in gravity. It's like a bigger mass is like causing a pull. But anyway, just a little example. And so if you think about gravity on the moon, it's smaller because the moon is smaller than the Earth. So that's why you see space people even kind of flow about very slowly because they're not falling as fast because the mass that is responsible for that falling is smaller. And that's gravity. Oh, and then the tides. So you can also think about this in tides. If you're a surfer, nobody in College Station because there are no waves or beaches, I think. You might want to look at how the tides are different based on the position of the moon. So the moon, its own gravity is going to cause like some sort of pull on the water on the Earth. So depending on its positioning around the Earth, then it's gonna cause the water to actually flow in a different direction. Because it has gravity pull, because it has gravity, because it has a large mass. I think that's all I was gonna say about this. Yeah. Okay, this is just a little joke. This does not explain why the gravity under your bed at 6 a.m. and 6 a.m. in the morning is so high and you just can't get out of bed. Gravity does not explain this, so if you want to get a PhD and figure that out, there you go. Okay, all right. So gravity. Have you guys heard the song by John Mayer? Yeah. I would sing it, but like no. I'm just gonna give some examples of this phenomenon, and here we have the merging galaxies, they're kind of bending in space on. Here we go. Planetary motion. Planets are gravitationally bound to their stellar system, so the sun. So we as Earthlings are gravitationally bound to the sun due to the sun's external gravity. And similarly, stars are gravitationally bound to the center of their galaxy. So this is like a big soup of gravitational equilibrium, right? And we live in a solar system, we're on planet Earth, orbiting around the sun, and the sun orbits around the center of the Milky Way. And so essentially all of us are gravitationally bound. So due to gravity that we're in this like somewhat stable equilibrium. Very important for how galaxies are. We also have gravitational waves. So this is again kind of showing this space-time continuum and how gravity or the mass of an object is like responsible for the movement of something in space-time continuum. So two, for example, neutron stars that are moving around each other can cause ripples in space-time due to their gravity. And then we have gravitational lensing, which you may or may not have heard of before, but this is also due to extreme gravity. And we can look at that in like a galaxy cluster. So when there's a lot of galaxies, and galaxies are very massive, like we live around a sun, and that's like something like 2 times 10 to the 30 kilograms. And then galaxies are composed of like thousands, millions of suns. Those are like a lot of weight, a lot of gravity to measure around that. So when there's a light that goes from behind a galaxy cluster, which is like hundreds, thousands of galaxies, that light is going to be bent, right? Like that's going to cause like bending of space-time, and the light is going to move around it. And you get something like this. And this is an observational image of space-time doing its thing in real time. So we're seeing galaxy light from a faraway object being bent by a galaxy cluster. And this also happens in this way. And doesn't you have to okay. All right. So this is another example of that. You have a galaxy behind a massive object, and the light is being bent due to the curvature of space-time, due to the massive object. Test it out yourself. Gravitational lensing in real life. So if you have finished that bottle of wine, you know, you might have finished with watching that Bachelor episode that sucks. Does anyone watch The Bachelor or The Bachelor? Just 3 people. Franklin, I need. Okay, so The Bachelor really sucks. It's like a TLDR. Don't watch it. But essentially, if you finish drinking your wine and you point your wine glass at a light, then you will see a bending of light, such as is described by the bending of space. And right, and so the most interesting part of this is that we're actually able to measure things in galaxies that are further away, because this acts as a magnifying glass. So we can measure things like their stellar mass. In some cases, the supermassive black hole. So we're actually able to learn about galaxies that are very far away because of this gravitational, like, magnifying glass, like galaxy clusters create. Okay. Whoa, black hole. Whoa. Okay. I mean, not since my talent, but okay. Black holes also cause things, gravity, because black holes are very dense, very massive objects. And so you can see here in this diagram, this bending of space-time. Black holes, it's so dense and so massive that it actually causes the fastest thing in the universe. It can't escape it. So, if you're on Earth and you want to escape the Earth's gravity, then you have to go fast enough to escape the acceleration that's pushing you toward the Earth. Okay, so there's an escape velocity, and that's how we get rockets on space. That's how we get our telescopes up there. It's going surpassing the escape velocity. However, for supermassive black holes, the fastest thing in the universe, which is the speed of light, cannot surpass that. They're black because they're the point of no return. So if you get close enough, you can't escape the gravitational pull. And that's how black holes happen, I guess. One way is stellar black holes, and this is due to the gravitational collapse. So the black hole can't physically sustain itself against its own pressure, and it just collapses into a black hole, causes immense gravity, no escape velocity, the fastest thing in the universe, that's black hole. And then supermassive black holes. These are like extremely massive. Okay, so stellar mass black holes are like hundreds of solar masses, which is, in astronomy terms, it means that you have the southern mass of the sun, so like 2 times 10 to the 30 kilograms, just a number. And then you multiply that by 10 or 100, you get a stellar mass black hole. You multiply that by a billion, tens of billions, and you get a supermassive black hole. And that's what lives in the center of our galaxy. And that's what was discovered by Andrade et al. And this was a long time ago, but they got a Nobel Prize in 2019. And that was measuring the orbits of stars around the supermassive black hole. And remember, a mass is responsible for how fast objects fall, how the velocity of things orbiting around. So they were looking at the stars and they were seeing some velocity, and they were saying something has to be responsible for that velocity. It's not just moving in space-time. That's not how Einstein's theory of general relativity works. And so then came, not then, it was already theorized before, but that was a way to prove the existence of supermassive black holes. By looking at the velocity and tracking these exact stars and how they orbit around the center. So this is really cool. Okay, my laptop's giving down. Okay. We also have an image from 87. We know that light cannot escape. We know that there's like a huge mass responsible there for the velocity of our objects. We don't see any light coming from it, and that's what we measure as astronomers. We measure light. So that's that. And now I'm going to get to my summary. I just want you guys to think about gravity in your day-to-day, just how light can be coming in one of these things. It's very important because it's literally what keeps us on Earth. It's described by any two objects with mass. So you and your other objects even have a gravitational attraction to each other. All right, and then but it really is just explained by interior relativity, which means that there's really not a lot going on if you're just like Cleveland, because you're not really that in space time. But if you're something like a supermassive black hole, you're causing like a huge bend in space time. And then just remember the black hole. And that's it. Any questions? Okay.
So I heard the sound of a black hole.
You know, I actually got to send that video. Someone sent me that video. I didn't hear that. I mean, yeah.
Yeah, I was gonna say.
I do not. Something that's competing against.
Well, not competing for much of there's a sort of a different theory than gravity that says that the way to think about being fragile or something being told is actually like that. Like when called third part of like the way you can think about is being forward that is actually static, pushing down.
Do not heard about that. I didn't think about gravity in the galaxy that which is people general gravity, but that's definitely something to do. I'll get into that. Yeah.
Structure black hole.
Oh my goodness. depends on the black hole that you talked about.
Well, very spot. You're very hard, very low.
Again, it depends on like the black hole that you're measuring, like inside of the black hole, I wouldn't be able to say like an exact, not an exact number, but it's comfort in any way, but because it's creating a lot of mass, they're like more, they're hotter, but if it's not, they're not as hot. So that varies, but the internal temperature of the black hole are not. Oh, no.
Very strong. I just want to know why I can't call him 6-2 first.
Wait, why you
I can't call him 6-2 first because I can't get out of bed because
somebody needs to get a PhD of that, back on one doctor. And it's really hard to get it out. But like, that's exactly what it is, 4 versus 1. Like, you're gonna be hard talking to them. Yeah, no. All right.
Thank you, Sylvie.
Yeah.
Okay, so now we are going to go over the trivia answers. And we have a winner somewhere. Yeah, I have it. There we go. All right, so the first question, what percentage of the mass of the solar system lies in our sun? The answer was A. 99.86% of our entire solar system is just contained in the sun. Question 2, what is the most abundant element in the sun? Hydrogen. What causes the aurora borealis and the aurora australis? C, the answer is C. It's B. Solar winds interacting with the Earth's magnetic field. This was one of the ones I got wrong. How hot is the core of the sun? I believe this one was also D. No, 25 million degrees Fahrenheit. I think D is very, very close. It's like 24.99999 million. Pretty close. Here we go. Fun fact. Answer B is how hot the corona is, or when you have a solar eclipse, there's a part that's very shiny around the sun that you can see. That is 3.5 million degrees. Question. We asked the nuclear physicists for their best approximation. And then we plug it into a computer, and the computer says, about this. 42 point something. You can also measure the radiation. In question 5, what is the name of the spacecraft sent to study the outer corona of the sun? Was the Parker Solar Probe. I know, everyone's super disappointed, I'm sorry.
So there's a little video here, if it'll play for us. So this is the video. This is the video that NASA released of the Parker Solar Probe. Parker Solar Probe flying into the sun. So what you're seeing here is one of these sides is, well, the side on the right is looking upward, like you can see the Milky Way galaxy just kind of flew by, you got planets and stuff going on. And then this left panel is inward. And then all these like streets are like highly energetic particles that are whizzing right through it. Super cool. Question number 6, how old is the sun?
Anyone?
Oh, Brad, to answer your question, black holes are cold. There's probably a firewall outside of the event, right?
So it kind of, I'll add to that question by saying Silvana also talked about a accretion disk. So I study what I call active galactic nuclei, which are essentially supermassive black holes in the middle of the galaxy that are rapidly accreting, so sucking in a lot of mass all the time, and they are insanely hot around the black hole. So it depends on what you want to call the black hole. Question from you? It's a boxer mix named Cleo. She will show you pictures. Cleo is about 60 pounds, and she was told that she was overweight. So she's been on a diet for a while, coming down, getting healthy.
The importance of mass is that she can curve space and time.
Yes. Make it harder for someone to get out of bed. We have life. Oh, we're up. Okay. All right, question number 7. The sun has a magnetic field, true or false?
False.
True. Question number 8. When does the solar eclipse occur? D. When the moon obscures the sun. Question number 9. Where does the sun lie in the Milky Way? How many of you got this right? I hope nobody said the very outskirts. Yeah, so this picture that you're seeing here, this picture that you're seeing here, this is called the Sagittarius arm, this guy, and then the Orion spur is right here. Oh, the other picture that she had there. Okay. We're right there. Take what I said and mirror it. Multiply by -1, it's fine.
That's the very outskirts.
That is not the very outskirts. That's the very outskirts. Question number 10, last question. I'm sure you're all sick of hearing my voice at this point. When will the next total solar eclipse occur in North America? April of 2024. I think it's April 8th, I believe, of 2024. It'll go basically right through Dallas towards the northeast. If anybody happens to be at Niagara Falls at that time, the path of totality will go right through Niagara Falls. So get married, get the honeymoon out of it.
Okay, so we have one winner, and I really hope this is your real name. But our winner was Tommy Hilfiger. Anyone? Tommy, who's not in the physics department. No one remembers putting Tommy Hilfiger as their name. Oh, and of course, it was one of my very good soccer friends whose children were tired. Too bad, Rob, you have to be here to claim your prize. Our runner-up was Erica. No, this is a family-friendly event. So Erica wins, yeah. Woo! Erica, just come see me for something. Your choice. A couple of quick announcements. Our next event is September 28th. If you are on YouTube, like and subscribe to our channel. If you are on YouTube, you should do it anyway. Please and thank you. It gets us views. Please don't forget to tip your bartender. And we're missing. Oh, and if you'd like to donate, please see either me or you can Venmo at AoT _BCS. $15 donation will get you a t-shirt, and a $10 donation will get you a free mug. Yeah, I think that's it from us tonight. And thank you everyone for coming out. This is one of the biggest times we've had. So thank you everyone. We appreciate it. Talk to your local astronomers, please.
Mind the glow sticks.